Okay, we're now going to look at rules of differentiation. Try to establish various rules for certain types of functions so that when we see them, we know what their derivatives are as opposed to having to use the definition over and over again. So we're going to apply the definition in our proof of these rules, and then from that point on, we will not have to use the definition. So here, the derivative of a constant function. If f is the function with the constant value c, and df dx, which is equal to the derivative of c, is going to equal 0. So we're starting here with a constant function, f of x equaling some value. The definition of the derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, since f of x plus h, no matter what we place in, we get c, we're going to be looking at the limit as h approaches 0 of c minus c over h, which would be the limit as h approaches 0 of 0 over h, and that limit is 0. Makes sense for us here. A constant function is a horizontal line. The derivative represents the tangent along the curve. Since it's a horizontal line, the tangent slope everywhere is 0. So if we have a function h of x equals 7, h prime of x by this rule will be 0. Or if we had a function g of x equals -3, the derivative of g of x everywhere along this function would be 0. Our second rule, the power rule for positive integer powers of x. If n is a positive integer, then d dx, the derivative of x to the n, is going to be n times x to the n minus 1, where we would plug in the appropriate values of n. So for this particular problem, let's start our proof by letting f of x be a general power function, x to the nth power. So by definition, the derivative of f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. In this particular case, that would be the limit as h approaches 0 of x plus h to the nth power minus x to the nth power over h. Now before we look at the numerator, let's take a look at an expansion from algebra. A to the n minus b to the n, a difference of 2 powers, is always going to factor into a minus b over times a to the n minus 1 plus a to the n minus 2 times b plus a to the n minus 3 times b squared. And it's going to continue on this pattern until at the end it's going to be a times b to the n minus 2 plus b to the n minus 1. So for our problem, what we have, a is x plus h, and b is x. So we can write this expansion as x plus h minus x. Then carrying out a few of the terms, we would have x plus h to the n minus 1 plus x plus h to the n minus 2 n times x plus x plus h to the n minus 3 times x squared And then at the end, we would have x to the n minus 1. The first part of our expression, x plus h minus x, is going to simplify down to just plain h. And then as h approaches 0, we're going to have our denominator of h. And then, of course, we're going to have that expression x plus h to the n minus 1 plus x plus h to the n minus 2 times x plus x plus h to the n minus 3 times x squared plus, and so on, x to the n minus 1 at the end. Now with our limit, as we look at it here, the h over h is going to reduce to 1. And since h is approaching 0, this expression is approaching x. So my first term is going to be x to the n minus 1. My next term, again, this is approaching x. So I have x to the n minus 2 times x plus x to the n minus 3 times x squared plus, and so on, x to the n minus 1 at the end. Now here, my first term will stay x to the n minus 1. N minus 1 plus 1. When we multiply, we add exponents. So n minus 2 plus 1 makes n minus 1. N minus 3 plus 2 makes n minus 1. And it's going to continue along that all my terms are going to be x to the n minus 1. So I'm repeatedly adding x to the n minus 1. If I were to go through and count them, turns out that I'm going to have n times. And so instead of adding x to the n minus 1 to itself n times, a quicker way of stating that is to write it as n times x to the n minus 1. So the derivative of x to the nth power is going to be n times x to the n minus 1. That means, so if we want to find the derivative of x to the third, well, in this case, n is 3, so it's going to be 3 times x to the 3 minus 1. So 3x squared is the derivative of x cubed. If we were taking the derivative, the dx means to take the derivative of, say, x to the 10th. The derivative there would be 10x to the 9th. So this power rule is a very big rule for us. It lets us take the derivative of powers of x. Let's move on to our next one, which is equally powerful, the constant multiple rule. If u is a differentiable function of x and c is a constant, then d dx, the derivative of c times that u, is going to equal c times du dx, c times the derivative of the u. So in this case, we're letting u represent some function. U could be x squared, u could be x cubed, u could be any function of x. So in this case, f of x is equal to c times some u, where again, u is a function. So when we take the derivative of f of x, we're going to look at the limit as h approaches 0. F of x plus h minus f of x over h. When we plug x plus h into function x, That's the same thing as putting the x plus h into that u and multiplying it by c. So we have c times u of x plus h minus c times u of x. The two terms have a common c. With limits, we can pull out that common term. So we'll pull out the c. So we have c times the limit as h approaches 0 of u of x plus h minus u of x over h. Now that particular expression looks familiar. Can't open it too well. But here we can compare. We have f of x plus h and f of x, which matches with the u of x plus h and u of x, matching h. This is equal to the derivative of f, because f was our function. That means that this expression is equivalent to the derivative of u. So we have c times the derivative of u, which is the same thing as c times du dx, remember, is the derivative of u. Now, how does this help us? If we happen to have a function like f of x equals 7x squared, seven is our c, x squared is our u. So we're going to take 7 times the derivative of x squared. We just learned that the derivative of x squared is 2x the first. So the derivative of 7x squared would be equal to 14x. If we're given a function g of x equals 9 times x to the 7th, our derivative is going to equal 9 times 7x to the 6th. 63x to the 6th would be the derivative. So not only can we take the derivative of expressions like x squared and x to the 7th, we can also take derivatives now when they have coefficients. And our last rule for today, the sum and difference rule. If u and v are differentiable functions of x, then the sum or difference are differentiable at every point where u and v are differentiable. At such points, the derivative of u plus or minus v is equal to the derivative of u plus or minus the derivative of v. So here we're going to take a function f of x is equal to two other functions. We'll call it u plus v. So when we find the derivative of f, we're looking at the limit as h approaches 0 of u of x plus h plus v of x plus h minus u of x plus v of x all over h. The limit continues. If we distribute the negative in the back and rearrange some terms, bring the minus u of x here. We have v of x plus h minus v of x all over h. With our properties of limits, we can extend this into two parts. The limit as h approaches 0 of u of x plus h minus u of x over h plus the limit as h approaches 0 of v of x plus h minus v of x over h. And this first expression is equal to the derivative of u. And this second expression is the definition of the derivative of v. So our f of x, our derivative of f of x, was equal to the sum of the derivatives of the two parts. In other words, du dx plus dv dx, using notation from Leibniz. U prime x plus v prime x is notation from Newton. Now here's what this allows us to do. If we have f of x equals x cubed plus x squared, we have two functions here. We have a u and we have a v. So our derivative of f is going to equal the derivative of u plus the derivative of v. The derivative of x cubed is 3x squared. The derivative of v is 2x. So the derivative of x cubed plus x squared is 3x squared plus 2x. If we have a function f of x equals 7x squared minus 5x plus 4, we could extend and apply the property here. Just treat it as three different functions instead of just uv, and w. So our derivative of f is going to equal the derivative of the first, which is going to be 14x. Remember, take 7 times the derivative of x squared minus 5. And then, of course, the derivative of the 4 is 0, so it doesn't show up. So along the parabola 7x squared minus 5x plus 4, the derivative is always equal to 14x minus 5, so that would be the slope of the tangent everywhere along. Now, if we want to find where we have horizontal tangents for a curve, what we're going to do to find the horizontal tangents will be to first take the derivative of our function. So let's say we have x to the second minus 4x plus 3. And look at the derivative. The derivative is 2x minus 4. Because it's a horizontal tangent, that means we want the derivative to equal 0. So 2x minus 4 would equal 0. 4 equals 2x. X is 2. So when x is 2, the corresponding y value is going to be 4 minus 8 plus 3, or negative 1. So at the point 2, comma negative 1, we have a horizontal tangent.